To be by Marron on going where no GC has gone before.
All right, thank you for the introduction. Exciting, yeah. So my name is Mark. This is some work that I did with Anthony over here. He's an undergrad researcher, did a lot of great engineering on this project. So, feel free to say hi to him if you have any questions about this. So, as the title says, this is a memory system for Bosque. And this is not just, this is the programming language we were doing, but a key part of this work is not just building a garbage collector, but what can you do building a garbage collector if you think about building the language as a co-design process, right? So I want to start off talking a little bit about what Bosque is and some of the features that are going to be particularly relevant to this whole concept. So at a high level, it's kind of a programming language and stack that was designed and optimized for reasoning. And when I say reasoning, what do I mean? I mean saying, if I give you a chunk of code, whether you're a human, you're a formal tool like a theorem prover, or you're an AI agent, we want to make it as easy as possible for you to look at that code and know what it can and can't do, right? What is it going to change? What is it not going to change? What is the output going to look like? What parts of memory is it actually going to touch, right? Now, usually when you come to an academic talk, the talk says, I have a cool new idea for a new feature or a new analysis that I'm going to take and I'm going to put on a language. I'm going to stack something bigger on top of this and add this on. Well, we take a totally different view, right? My version is we're reaching a critical point in programming languages. We have this sort of JavaScript, Java, Python family of languages that have been around for as long as I've been a computer scientist. We've added more and more features, and they're just starting to creak. And we're at a point where there was going to be a new paradigm shift to new ways to think about programming language design. And this is kind of Bosque's a stab at that, where we try and tear out anything that might have made sense 30 years ago, but just requires some rethinking today. So we're going to simplify everything as much as possible. I'm not going to add anything new. I'm not going to solve complexity by adding new complexity, and we're going to see where that gets us. So what do I mean by simplify? I don't mean I'm only going to have one keyword or there's one operation that does everything. What it means is I'm going to look at foundational sources of complexity, maybe accidental complexity or implicit complexity, that just seem to complicate life when you're building a compiler, when you're building a runtime, that every time you have a research project that starts out with a great idea and then you're like, oh gosh, we're doing loop invariance again, right? And everything runs into a wall. So there are four big things that we got rid of in Bosque in the core. No loops, right? It's immutable, fully referentially transparent, pure, right? So it's very easy to reason about, no frame rules, no non-monotone reasoning, no inductive invariance on loops, all that good stuff. And two key things for this talk: it doesn't have you can't build cyclic data structures. It's impossible in the design of the language. And the semantics are fully deterministic. So there is one and only one possible output for any computation, guaranteed. Right? And the other thing we do is we just try and make as much information explicit that's usually implicit. Like if I'm looking at a C code base and I want to call a function or create an object, I need to kind of wonder, like, what is the implicit invariant that I need to preserve about this object in order for something to not blow up elsewhere? And so I need to look at out-of-date documentation, try and find the coworker who wrote that code a month ago, rummage around the code base and guess. We want to take all this implicit knowledge, put it in a very explicit form that is compiled and put right in the source code as a first-class artifact. So there are a lot of words here, but let me show you kind of just a little bit of code. So here's one example. Even though we have this very nice functional core, the goal is to make this very accessible to a modern dev coming from TypeScript or Java or something. So here's an absolute value function in Bosque. It's not functional. Even though the core is functional, we have block structures, we have variable reassignment. Developers want parentheses, give them what they want, right? Make them very happy. You can see we make this implicit information explicit, ensures, requires, inductive data invariants are all part of the syntax of the language, but it's very natural for someone who's a modern developer. We have a lot of nice affordances like spread and rest, higher order functions for doing data processing over collections rather than writing loops with off by one errors and all this stuff. So pretty nice language there. And we spent last summer, we wrote around 25,000 lines of Bosque. We were like really excited about this. We're like, okay, let's build this and actually start getting some users and start really pushing forward with this. And that means we need a GC, right? We can't use a slow interpreter and just rely on the JavaScript collector anymore. So I'm coming from, you know, cloud dev experience. I spent a lot of time working on Node.js, working with folks in the JavaScript team at Microsoft, seeing all of this community, the serverless folks, what they were doing. And I noticed kind of some differences from what I would call classical GC systems, where it was a huge machine and the emphasis was really on throughput of batch processing and jobs, right? In this space, people were really worried about startup. Like, I'm scaling out rapidly. I need my applications to start up very fast. I'm responding to short user requests, so latency is critical, right? Like, my 95 or 99th percentile is more important than getting the max throughput of the system, right? Because that's where I lose customers when it takes 2 seconds to respond. And of course, memory footprint. I'm scaling out, I'm packing a bunch of these things on a machine, and of course it costs an extra $1 for each machine and each extra VM I spin up, right? So this was kind of why I wanted to think about, like, let's optimize the GC for this. And interestingly, this is also seeming to become very important for agentic style applications that have a lot of this rapid scale up, scale down behavior. And of course, you know, the interesting thing for me is a lot of times when you think about building a GC, right, there's this sort of, I have 3 things I want. I want good latency, good throughput, and no starvation. But there's trade-offs between these, and if I optimize one, I lose on another. So I kind of have to, I want 3, I choose 2, right? And conventional wisdom kind of suggests that that's just the way life is, and you sort that out. Now, interestingly to me, when we were getting started on this project, there was a paper at Uppsala Splash last year that they had a little proof that says this is not just a gut feeling, but this is in fact theoretically impossible to have all 3 in a language that has both mutations and cyclic data structure. So it's sort of an impossibility result for any existing language, almost any existing language today, that you could have a GC that satisfies all 3. But conveniently for us, Bosque actually is immutable, so no mutation, and cycle free. So the question is, can we do better in Bosque, right? Can we actually build a GC that satisfies all of these desirable properties simultaneously? And, you know, spoiler, or maybe not a spoiler because I'm giving the talk, yes, we can, right? So how do we do that, right? That was the next question. And I thought back to a couple papers that I really liked from, wow, 2023. That's an autocorrect that's not right. From 2003. Both of these papers are from 2003. And they both talked about a similar idea. And it basically boils down to this. If I look at how object lifetimes go along, I kind of have young objects that are very hot, allocated quickly, touched a lot, die young, right? And then I have older objects that hang around for a long time, get kind of cold or touched infrequently, and will probably live for a long time. And with this sort of bimodal behavior, does it make sense to use the same collector algorithm for both families of objects? And the answer was no. Let's try and pick a collector that works well for the behavior of each class of objects, and then put those objects in that part of the heap, right? So we use copy and collector for the young nursery, and we use RC for the old space. And this seems like a great setup, and very cool. But the results were good, but not phenomenally better, right? And kind of the problem was, well, your latency gets better because you aren't doing a bunch of old heap traversals, except every now and then, since RC can't collect cycles, you need a backup cycle collector that does need to traverse the whole heap. So on average, your latency gets better, but you still have a high 99th percentile latency when that cycle collector has to kick in, right? And you get better mutator throughput, but you still have some slowdown because those RC objects, although they usually aren't touched much, sometimes you have a bit of code that goes and does a lot of mutations on old objects, right? Which require a bunch of RC updates and a bunch of memory, remembered set entries, because you now need to reprocess these, and then you have a larger young processing time. So you things are better, but they're not awesome, or as good as you might expect. And this this line of work kind of hovered for a while. So what do we do? Well, now we know we have no cycles and we have an immutable set of objects. So the question is, how do we take these existing algorithms and how do we not add a cool new feature to them, but how do we simplify them and eliminate all of these extra complexities and actually get them down into their high performance essence, right? So we want to go a little further, because I just kind of like conservative root collectors, because I'd really like to set this up where the mutator, the application code, doesn't have to worry about interacting with the GC code almost anywhere except where it wants memory, right? So we're going to do a conservative root set, so we don't have to do stack maps. We don't have to worry about pointers to internal references, no safe points for synchronizations if we have multi-threaded collectors. And in fact, each thread can sort of run its own allocator and most of its collector entirely independently. So this allows us to scale up and scale down on threads, I think, a lot nicer. We haven't really evaluated that yet, but I'm optimistic. So it's a really simple algorithm once you've distilled and simplified it a lot. So I'm not going to go into a lot of detail, but I'll just walk through an example so that we all are on the same page. So here we have a heap. We have a set of roots. They can point back to themselves. They can point to some young objects, some old objects. Young objects can point to old objects, but since we can't mutate old objects, we can never get any old to young pointers. So we don't need any remembered sets. We don't need any write barriers or anything, right? This is great. It makes our life a lot easier. So for collection, we start from the roots. We go and we mark the young objects. Anything that's young, we'll mark and get ready to evacuate, but we don't need to walk any of the old objects because they're all reference counted, so we just stop there. So the only thing the mark and evacuate phase has to do is touch the nursery. Then we go ahead and evacuate all of those young objects. Since we're a conservative scan, if we're pointed to by a heap object, we just have to promote it in place. If it's only pointed to by objects from other, or pointers from other objects, then we know those are precise, so we can evacuate it, so we get the benefits of most of the benefits of a copying collector and compaction and memory reuse. We'll go and do our RC increments on all the objects now that they're in the old space, and then all we have to do is go ahead and reclaim the young space and do any RC decrements, and that's it, and our collection's done and we're ready to allocate again. So very simple, not too hard, still managed to have plenty of bugs in there. It's garbage collector code anyways, always, so there's always fun bugs. But the interesting thing is, the thing that's really cool is, we can have it all in a sense with this algorithm and this language. So we're guaranteed bounded pause times, because we will only, on a collection, we'll only have to go and sweep the young space. And we don't have any remembered sets, so we don't have any extra stuff that the mutator can create extra work for us, right? So our pause times are bounded by that young space collection. We have a pretty high throughput because we aren't touching objects repeatedly, right? We aren't going to basically mutate an object and then have to rescan a whole part of the heap, right? Or we don't have to do repeated RC inks and decks because we're traversing some part of the old heap, right? We only do inks and decks proportional to the number of allocations. We're free of starvation because each collection will collect all of the nursery plus whatever was released in the RC space. So we're guaranteed to get enough memory on each collection to satisfy all requests until the next collection. We can never be outrun by the mutator. And the other great thing is, since our heap, the old RC heap, is basically, anything that's alive in there has to be used by the application. So that's tightly bounded in the amount of memory overhead. And then the nursery is a fixed size, in our case 8 megabytes. So we don't have to do a 1x, 2x, 4x of the live heap size, right? The amount of heap we use is the live heap size plus the constant nursery overhead. So we have a very efficient memory footprint in the collector memory usage, okay? One thing that I thought was also very interesting about this is when the collector runs, since it only has to scan the young space and then touch objects in the old space that were referenced by young objects, we only touch the young space plus this old space fringe. So the collector will never go and traverse large parts of the heap that are cold and thrash out whatever objects or memory locations the application is touching. So we get a very nice memory pressure happiness result there as well, that we never thrash the application cache. So this was very, very cool, sort of a bonus feature. Okay, so theoretically this was all very nice, but we wanted to do an implementation to validate that in practice things matched, right? So as I said, our goal was simplify. So the allocator implementation, collector implementation is actually pretty small, about 2.4 kilolines of code. Not very optimized yet. They're just standing it up, so lots of room for improvement. Still bugs. I was fighting one yesterday, but enough confidence to run things. Our default configuration is an 8 kilobyte page with an 8 megabyte nursery fixed. We're running this on an AMD, with 64 gigs of memory, so plenty of space there. Now, one of the challenges of this language in runtime co-design is you've got a new language. It doesn't have a lot of code established. So our benchmarks are a little small, so I don't want to oversell this as a definitive result, but I think it's indicative that the theory and the practice are consistent, right? So our benchmarks range from about 200 to 5,000 lines of code written in Bosque. When we run this, the GC overhead's about 7% overall. We kind of tuned for that. So not great, but pretty decent. And we have these benchmarks. And as you can see, if you compare our collector Pando with an Epsilon GC, which does no work, we are actually much faster because we get far much better cache locality, but a good sanity check that the cost is not crazy. But to me, more importantly, is the pause times that we see in the collector at the 50th percentile level are very small. This is in microseconds. But also that they stay very constrained going up to the 99th percentile. So we see a very low, sort of variability in this behavior, which is exactly what we wanted for nice, predictable performance in the overall application there. Now, we did want to do a little comparison with an existing Java application. Now, we went to NBody, which has everybody's favorite benchmark, binary trees. Everybody uses this. It's one of the great JavaScript benchmarks. And basically, it just creates a lot of binary trees, some that live a long time, some that die along quickly. It's designed to stress the garbage collector. And the nice thing is, you can write exactly the same code in Bosque and in Java. So it says apples and apples comparison you can get, even if the benchmark is a little simple. But at least it gives us a sanity check. So we went and ran this benchmark with ZGC, Shenandoah, and Pando. Now, as you can see, if we turn the heap up to an unlimited amount for whatever the application wants to use, Shenandoah and ZGC are much faster on this. They take about 2.5 seconds. We take about 6 seconds. So clearly, our GC is not as performant as these very well-engineered and optimized systems, but at least not embarrassingly slow. Now, what was interesting here is one of our claims was that our memory footprint, our resource requirements were very constrained, and we did not see significant performance degradation in that constrained runtime. So we turned the min heap down to 1.5x to see how this looked. So for our system, behavior is totally unchanged, right? Because the memory it needs is the actual live heap plus that overhead given by the nursery. So we perform just as well. Whereas ZGC and Shenandoah obviously struggle some more, right? They hit these limits very hard. They run into degenerate collections. Their latency goes up, and they have to spend multiple threads, to get collection to keep the application from starving. Now, the wall clock time still outperforms us, like 4.7 to 5.9 seconds. But if you look at the CPU time, you can see that they've really pumped up the resources to do these massive parallel collections, right? So it actually, the cost is pretty high. Okay, so what to take away from this? Well, I think one thing is, hopefully you say, oh, this is a cool GC and a cool language. I think it's really neat to see that you can avoid some of these impossibility results by not just trying to engineer more in the GC, but think more broadly about the ecosystem and the problem. So that kind of leads me to the second thing. I think this is maybe, this result I hope is exciting to you, but I think also maybe this encourages the community to think a little bit more about what this space of language design is and how it opens up more possibilities for runtime system development. I think this is a really interesting time, this disruption of LLMs and the need for people to write languages that support not traditional workloads, but these LLM, AI, agentic style workloads. And I also see this as an important time for our community to kind of step in and, in industry, oftentimes a problem comes up and it needs to be solved in 3 months. And that means it's time to grab whatever is there and make it work. And what I would hate to see is for people to grab JavaScript, put a new coat of paint on that, and us to be stuck with that for another 30 years. So I think this is a great opportunity for us. This is a crisis point in programming languages for us to step in and actually show some interesting points in this design space. So when people need to grab stuff, there are good things for them to grab and build a future that allows us to be innovative and creative and really where we want to be. So I'll wrap it up with that, with a couple links to some of these papers I mentioned, and a link to the Bosque language programming repository if anybody wants to poke around or take a look at stuff there. And I think I have a couple minutes for questions.
50 minutes questions. So I have a question. So when you're doing the collection, isn't it possible that you could end up collecting a lot of the old heap? Because if a lot of it becomes unreachable at that point.
The RC space? Yeah, so what we do is we basically have just a little, we time box that and then have basically a pending deletion list that we thread through there that we will then heartbeat off. So we will gradually reclaim the RC space. If you have like a catastrophic deletion style thing, yes.
Hi, I just wanted to point out some super cool work by that guy over there, Matt Parkinson, about basically doing reference counting with immutable cyclic garbage. So you could be able to have free cycles in your Bosque language and still, I think, retain many of these properties. Right? You do a nice SCC analysis of all the objects that are connected together in an immutable cycle, and they have all the same lifetime. So that would be an interesting opportunity for you to possibly look at that work. Yeah, for sure. I think our goal here was just get a plausible baseline to validate this. But we definitely have some stuff in terms of better SCC collection, in terms of better multi-threaded collection. And we'd also like to do, there's always an issue of fragmentation, right? Especially since we have a conservative stack. So can we basically use similar ideas of leveraging features of the runtime to be more aggressive in doing our compaction on on fragmented objects, right? So specifically, we have this very nice feature that things are fully referentially transparent. So you can't tell if you point to the same object or different objects. And so in a sense, if we don't have this concern of atomicity, so we can basically move an object, forward your pointer, and it doesn't matter if you have 2 copies of that object, eventually we move them together, you're confluent in your rewrites, and you don't care. So we don't have to do a bunch of atomic coordination. So we think there's a lot of other interesting possibilities here that we definitely want to explore once we just sort of bootstrap up a little bit. Yeah.